All right, we're getting into series and summation notation today. So a series, you are taking that pattern, that sequence like yesterday, and you are adding all of those terms together. So again, there's a finite series where it's just a limited number of terms that you're adding together. And there's also an infinite series that goes on forever. Now those are impossible to add up together, so you wouldn't be doing that. If you look, this is what summation notation looks like. It looks like this cute little E here. And in this E, it has some different parts. That E means like the sum of. So if you look at the bottom, it doesn't necessarily need to be I. It can be whatever number or whatever variable, but that's like the term number. So yesterday we were using n's. You could put n equals, but this is like your lower limit. It's saying starting with the first term, and then the top of the E is like the upper limit. So we're taking the first term all the way up to the fifth term, and we're going to add them together. And then on the right side, this is like the rule. It's like the equation almost. So yeah, we're gonna do it. We're gonna do it right now. Let's get into it and we'll have some fun using summation notation. All right, so we are gonna write each one in summation notation. I think your favorite part of this is gonna be writing that cute E. So the bottom of the E is like, what term are you starting with here? And for us, if we're generating something in summation notation, we're always starting with the first term. So again, you could choose any letter. Because the previous one had I, we'll just do I. So we're starting with the first term here. The upper limit is how many terms do you see in this sequence? I see 1, 2, 3, or sorry, series. I think I said sequence. There are 5 terms that we're adding together. So the upper limit would be 5. And now on the right side, we come up with a rule for that. So again, basing it on the term number. Is there any relation between 1 and 3, 2 and 6, 3 and 9, 4 and 12, 5 and 15? It's always the term number times 3. So if the term number is represented by I, we would just say I times 3 or 3I. That's it. All right, the second one. So let's look at our term numbers. We have 1, 2, 3, 4, 5. There are 6 terms. So our lower limit's always going to be 1 when we're setting these up. In this case, it was 6 terms total, and now we need to come up with a rule for that. Now, I do notice that it's alternating positive and negatives. Yesterday we wrote a rule for that. Now, if it is starting negative, and it alternates, you just say -1 to the n power. If it was starting positive and then flipping negative positive, then you would do -1 to the n plus 1. It's such a pain. But all right, times, and that handles the positive negative thing. Now we can just look at the numbers. What's the relation between 1 and 2, 2 and 4, 3 and 6, 4 and 8? It's always just the term number times 2. So I times 2 is 2I. There it is, folks. There it is. All right, let's look at this thing. Goodness. We have our first term, second term, third term, fourth term, fifth term. So let's see. Our lower limit, we're starting at 1. This has the ... The ellipses means this pattern goes on forever. There is no upper limit. So we're going to represent that by saying infinity up there. Cool. Now, something I notice is all the numerators are always 2. That's fun. 2 over. Now let's look at the denominators. We have 4, 9, 16, 25, 36. Something that pops into my brain are like, those are all perfect squares. There's some number times itself gives you that number. Like 4 is 2 times 2. 9 is 3 times 3. 16 is 4 times 4. 25 is 5 times 5. This is 6 times 6. So now looking at that pattern and the term number, the first term is 2 times 2. Second term, 3 times 3. Third term, 4 times 4. So it's always one number larger than the term number squared. Here's how we're going to represent that. One number larger than the term number we could say is n plus 1, and we need to write this as squared times itself. So we could just say n plus 1 squared. Put it in parentheses. Again, it's a little puzzly. You got to kind of figure out what pattern works for all of them here. All right, let's look at our terms here. 1, 2, 3, 4, 5, 6, and it goes on forever. So we'll say I equals 1, and there are infinite terms here. Now it doesn't alternate. Oh, thankfully. Let's see. I see 1 times 2 is 2, 2 times 2 is 4, 3 times 2, oh, is not 8. But as we go down the line here, I see that it's multiplying by 2. If that is the case, I start thinking of 2 as the base with an exponent on it. And our exponent would be based around the term. So like if I'm looking at the first term, is 2 to the first power 2? Yeah. Is 2 to the second power 4? Yes. 2 to the third is 8. So it's always 2 to the term number. Boop. 2 to the n. And this is just like, you get in the flow once you do a few of these. It gets really fun and exciting. Really fun. Now we're going to evaluate some of these. So they're going to give it to us in the summation notation, and we're going to have to add. Remember, these series, we're adding the terms together. So we're going to start at the first term, we're going all the way to the sixth term, and we're going to add them together. There it is. Here we go. So this is saying that we're, what? I don't know what that was. This is saying that we're starting with the third term, we're going all the way to the sixth term, and we're using this pattern, 1 over 2 to the term number. So when we're doing our first term, or sorry, our third term, that would be 1 over 2 to the third. And we're going from the third term to the sixth term. So the fourth term would be 1 over 2 to the fourth. Fifth term, 1 over 2 to the fifth. Sixth term, 1 over 2 to the sixth. And we are going to add these all together. Now, 2 to the third I know is 8. So this will be 1 over 8. And they're just going to keep going up by a multiple of 2. So 8 times 2 is 16. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. Now when you're adding or subtracting fractions, you have to have that same denominator. Luckily, as we went down the line, we were just multiplying that denominator by 2. So if we backtrack 1 over 32, we can make it 64s by just multiplying by 2. So this would be 2 over 64. So we could double this. That would be times 4 times 4. 16 times 4 is 64. So we have 4 over 64. And then if we're making eighths, 64ths, times 8 times 8, 8 over 64. Now that they're all 64ths, we can add them together. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15, and you can't simplify that anymore. Woohoo! That was fun. That was real fun. Let's see what else we got. All right, here's our rule. 10 minus the term number squared. We're starting with the first term, we're going all the way to the fourth term, and we're going to add those up together. So writing this one is kind of the biggest pain. It's not terribly difficult math. But the first term, we're going to have 10 minus 1 squared plus 10 minus 2 squared plus 10 minus 3 squared plus 10 minus 4 squared. Now you don't need to put those in parentheses. It's usually a good idea, but it won't make a difference. So 1 squared is 1, so we have 10 minus 1. 2 squared is 4, 10 minus 4. 3 squared is 9, 10 minus 9. 4 squared is 16, 10 minus 16. And this should be pretty easy what we have left. 10 minus 1 is 9, 10 minus 4 is 6, 10 minus 9 is 1, 10 minus 16 is negative 6. If we're adding these together, 6 plus negative 6 cancels out, so we just have 9 plus 1 is 10. That wasn't too bad, right? Wasn't too bad at all. I think we have 4 of these total. Oh yeah, and that fourth one's a real doozy. Here we go. See, we're doing 2k minus 1. 2 times the term number minus 1. We're starting at the first term, we're going to the fourth term, and we're going to add all those together. Now some people like to stack them on top of each other. I'll show you what that looks like. Like we could do 2 times 1 2 times 1 minus 1. Then we could do 2 times 2 minus 1. 2 times 3 minus 1. And 2 times 4 minus 1. This will work. And then we can just kind of add that last column. 2 times 1 is 2. Minus 1 is 1. 2 times 2 is 4. Minus 1 is 3. 2 times 3 is 6. Minus 1 is 5. And 2 times 4 is 8, minus 1 is 7. And we're going to take these totals back here, and we're going to add them together. So 7 plus 3 is 10, 1 plus 5 is 6, 6 plus 10 is 16, or you can add them whichever way you'd like. That's just what I did in my head. Okay? Great. One more. Negative 5 times 2 to the k minus 1. We're starting with the first term. We're going all the way to the fifth. If you'd like, you can do what we just did. Stack them vertically. Negative 5 times 2 to the 1 minus 1. Let's just go ahead and do that. You do the exponents first. 1 minus 1 is 0. I know anything to the 0 power is just 1, so negative 5 times 1 is negative 5. There's our first term. Our second term, we would do the exponents first. 2 minus 1 is 1. 2 to the first power is just 2, so negative 5 times 2 is negative 10. The third term, 3 minus 1. Exponent, 3 minus 1 is 2. 2 squared is 4, so negative 5 times 4, which is negative 20. We're going all the way to that fifth term. Negative 5 times 2 to the 4 minus 1. 4 minus 1 is 3. 2 to the third is 8, and negative 5 times 8 is negative 40. Also, you might notice a pattern back here. Negative 5 to negative 10 to negative 20 to negative 40. The next one's probably negative 80, right? It's getting multiplied by 2. All right, that last term. 5 minus 1 is 4. 2 to the fourth is 16. Negative 5 times 16 is negative 80. Now we do have to add all these together. Luckily, since they're all negative, we can just add them together as if they're positive numbers and make it negative. 80 plus 20 is 100. 40 plus 10 is 50, so 150 plus 5, 155. So negative 155. That's it, man. We're done with series and summation notation.